Let's imagine a gas enclosed by this black box chamber that I've shown in this picture. So the gas is represented by all these little green dots. And all these dots are in random motion. Some are moving slow, some are moving quite quickly, and they're bouncing off the walls of the vessel itself, creating a pressure. Now we just learned that if work is applying a force over a distance, if I push on this little red piston at the top that is free to move up and down on this gas itself, if I push on it downwards, I must apply a force and I end up squeezing the gas. And if I do that, I should do work on the gas. So we showed that work is change in pressure times volume. We've already looked at the units and the dimensional analysis to show you that pressure times volume is actually in fact joules. So if I change the volume of that gas by squeezing that piston, I in fact am doing work on that gas. And we should be able to show that this is actually true using our PHEt simulation. Before we begin the simulation, let's just have a look at our equation in a little more detail so we know what we can look at and what we can expect from the simulation itself. Change in pressure times volume can be written as follows. Pressure times volume final minus pressure times volume initial. Just like any change in physics, it's final minus initial. Now, we've already seen that the kinetic energy of a gas can be calculated by looking at its temperature only. The average kinetic energy in any gas is 3/2 times Boltzmann's constant times T. Now that's for an individual molecule. That's not the overall energy of the gas. That's the average kinetic energy that those molecules possess as they're moving around in random motion. The overall energy would be simply the average kinetic energy that we've looked at above multiplied by the number of molecules inside the gas at that time. So the total energy of the gas at any given point is simply N times the average kinetic energy. Now once again, this is the average kinetic energy per molecule. So really what it's telling you is the average energy for one molecule only inside that gas. So if we want to get the total energy, we would simply multiply this formula by N. So our total energy equation ends up looking like this. And we use the symbol U for the total internal energy of a gas. It'll just be N times 3/2 kT. Now the main thing for us is that we can actually see if the internal energy of the gas changes by simply looking at the temperature, because we can see from that equation that the internal energy of a gas, which is U, is proportional to the temperature, the absolute temperature in Kelvin of the gas itself. So if the temperature increases, then the internal energy of the gas must have increased as well. Now let's look at these relationships in a little more detail using our PHEt simulation. So here's our PHEt simulation, properties of a gas, or gas properties as it's called on the website. We're going to leave the constant parameters to none. Okay, so we're starting with an empty chamber. My initial volume, remember, is represented by the length of this chamber for those of you that have done the lab. And that's simply because the cross-sectional area of the box itself does not change. So if I change the length, I am in fact changing the volume. And it's directly related. Half the length, if I go from 8 centimeters here down to 4 centimeters, will be half the volume. So we're going to use this number measured right on the ruler as our volume measurement, because it's directly proportional. So I'll pump some gas into the chamber and let it reach equilibrium. And we can see that initially the temperature of those molecules, which is proportional to the average kinetic energy, is 300 Kelvin. And if we wanted, we could calculate the total internal energy of that gas based on the equation we just discussed. 3/2 times the number of molecules times K times T. And we even have the number of molecules in this simulation. But honestly, it's not necessary for what we're trying to do. We're trying to show you that if I squeeze the gas, we do work on the gas. We're changing its energy. So initially my volume is 8, and we're going to let our pressure stabilize. And if you recall, work is change in energy, and energy in a gas can be represented by pressure times volume. So my initial pressure times volume reading, we're going to say, is about 0.61 times 8 centimeters. So if I grab a calculator and work that out, if I go 0.61 times 8, 4.88, and now we can't say joules, remember, because we're not actually measuring a true volume there, but 4.88 is my initial reading. So let's tuck that away for a second. 4.88. Now I'm going to squeeze the gas, and I want you guys to notice what happens to the temperature of the gas when I do it. So I'm going to take it from 8 centimeters down to 6. So I'm going to move this wall all the way to the 2 mark. And when I do that, notice that the temperature rises. It goes from 300 to 481 Kelvin. And since the internal energy of the gas is directly related to temperature, we know that the internal energy has gone up. Now it's reached a new pressure here. So if I recalculate my pressure times volume, this one we're going to go 6 times 1.35. .1. So clearly I've done some work on that gas. PV after is greater than PV before, and you'll recall that PV measures energy. So my energy has changed. So if I squeeze the gas, I must have done work on the gas. Evidence for that is P times V has increased. But more importantly, the internal energy of the gas, which is represented by the temperature, has also gone up to 481 Kelvin.